The frequency of a sound wave can be affected by a myriad of circumstances and variables. In an attempt to measure how two of these affect the frequency of a specific type of wave, we conducted an experiment through which we could scientifically prove this.
The specific sound wave we tested was that created by the resonance of a wine glass. It is a well-known fact that the resonance created by a wine glass changes as the wine glass is filled with more and more water. So we decided to test the frequency of 4 different glasses: a red wine glass, a white wine glass, a brandy snifter, and a champagne glass.
To do this, we use the following equipment: a 30cm ruler, the 4 wine glasses, an iPhone 4S to record the audio, Audacity to analyze the audio, and Logger Pro to be able to fit a mathematical equation into our data.
Our method processes the following. Step 1. We recorded the resonance of every glass using the audio recording app, Voice Memos, found in a regular iPhone 4S. We recorded every glass 9 times, increasing the water height by 1 centimeter each time. Step 2. We transported the audio to Audacity, where the resonance frequency was measured in hertz. Step 3. We used all the data to make a graph for each glass that compared the change in frequency with the change in water height. We fit a model into this data using Logger Pro.
After analyzing the data we collected, we were able to make several observations regarding the resonance of each different wine glass and how it relates to its shape. The white wine glass proved itself to be one of the highest frequency range, with a maximum frequency of 1380 Hz and a minimum of 934 Hz. The glass with the second highest frequency range was the champagne glass, with a maximum of 993 Hz and a minimum of 582 Hz. After that came the red wine glass in the third highest frequency range, with a maximum of 807 Hz and a minimum of 447 Hz. And finally, the lowest frequency range was a brandy glass, with a maximum of 537 Hz and a minimum of 228 Hz.
Our results led us to many conclusions. First of all, we learned that the shape of a wine glass does affect the frequency of its resonance. A wider glass, like a brandy snifter, will have a lower frequency range, while a thinner one, like a champagne glass, will have a higher frequency range. We also learned that the height of the glass is also relevant to the frequency range, because the champagne glass was taller than the white wine glass, and it had a lower frequency. Through the conduction of this experiment, we also learned that as the wine glass fills up with water, the frequency of its resonance becomes lower. This phenomenon is counterintuitive, as we are accustomed to thinking that smaller objects and spaces yield higher frequencies.
There were many ways in which we could have improved our experiment, but overall we got accurate data and the results and conclusion were satisfactory. Going into our research methods, we could have improved by using a recording device of a higher quality than an iPhone 4S and recorded the audio in a more suited environment, for example a music studio with soundproof walls and professional microphones. Our data does not show high error margins, but this probably originates from the recording, which was conducted on the SFG High School library. For all the 4 wine glasses, we were able to observe that as the amount of water increased, the frequency decreased. Having done research on this matter, we have come to understand that there is no discovered reason that proves why an increase in the water height makes the frequency lower.
Although sources of error could be many, from the recording device we used to the methods through which we obtained the resonance, the obtained results were satisfactory and fit the model accurately. With this data and the model, we were able to understand how the resonance of different wine glasses is affected by the glass shape and water height.